I'm going to briefly present the EARLINET measurement campaign during the COVID-19 lockdown period in Europe in May 2020. So the campaign was organized within the EARLINET and ACTRIS, and the main goal was to study the tropospheric aerosol change during the COVID lockdown. I'll try to be very brief, and at the beginning I will just give a short information about the EARLINET, European Aerosol Research Lidar Network. Then I'll just give a few information on the Belgrade Lidar Station. After that, I will present the basic information on EARLINET measurement campaign and the preliminary results and experience we had, and of course ongoing and future research based off the observed experience. As you know, European Aerosol Research Lidar Network, called EARLINET, was established in 2000 as a research project with the main goal of creating a quantitative, comprehensive, and statistically significant database for the horizontal, vertical, and temporal distribution of the aerosol on the continental scale. Currently, there are 31 LiDAR stations within the network, and since 2000, EARLINET has continued to provide the most extensive collection of ground-based data for the aerosol vertical distribution over Europe. As we all know, atmospheric aerosols are considered as one of the major uncertainties in climate forcing, and it's really necessary to understand in details aerosol characterization and their role in the atmospheric processes. The most significant source of uncertainty is the large variability in space and time of the atmospheric aerosols due to their short lifetime. So it's very important to understand and to observe the vertical distribution of the atmospheric aerosols, and it seems that LiDARs and remote sensing are the most appropriate tool for providing this information. The data set observed by EARLINET are used to validate and improve atmospheric models. I will just give a short overview of the LiDAR technology. LiDAR stands for light detection and ranging, and usually the LiDAR consists of two parts, emitting and detection part. Emission parts consist of laser, which emits the short pulses with high frequency, and after interaction with the atmospheric aerosols, we can collect the backscatter radiation using different types of telescopes and detect the signals using usually photomultipliers working on analog and photon counting mode. So basically it's very simple, very similar to the radar technology. Here is the presented the major parts of the LiDAR system and characteristic signal response. As you can see on the right panel, characteristic LiDAR signals at the beginning, it started to increase, and at the moment where the laser beam enters into the telescope field of view, the signal started to decrease. And of course, at a certain height, where there is an aerosol layer, we can observe the intensity increase. So this is standard or characteristic LiDAR signal. From this signal, we are able to calculate different optical properties and the vertical profiles of the atmospheric aerosols. And I will just give a simple basic LiDAR equation just to illustrate the major optical properties we would provide with these kind of measurements. I will not go into the details in this equation, but the major optical properties of interest are aerosol backscatter coefficients and extinction coefficients. So these coefficients are directly related to the atmospheric concentrations, and of course they are depending on the wavelength and of the chemical components of the aerosols. Here is just a graphical representation of the LiDAR equation, and I would like just to point out the importance of the duration of the laser pulse, why it is necessary to be very short pulses because of the scattering volume. So we have the shorter pulse duration, we can obtain the aerosol layer position with a high accuracy. In this slide, I would like to present the Raman LiDAR station in Belgrade. As you can see on the map, the Belgrade Raman LiDAR station is the unique station in this region in the Balkans. So it's very important to provide regular measurements and to provide information of vertical distribution of the aerosol in this region. Just a short overview. This is a Raman LiDAR. That means that we are able to detect elastic wavelength at 355 nanometers and the Raman channel at 387 nanometers. The detectors are photomultipliers operating in analog and photon counting mode. And very important information is that the spatial resolution is 7.5 meter. That means that we are able to provide information on the vertical structure of the aerosols with this resolution and up to 15 or 16 kilometers. As a part of the EARLINET joining LiDAR station, the main goal is to become a member of ACTRIS. EARLINET is a member of the ACTRIS. ACTRIS is Aerosols, Clouds and Trace Gases Research Infrastructure. So this is research infrastructure in Europe, which is in implementation phase, and it's going to be the basic infrastructure for atmospheric research related to aerosols and trace gases. So ACTRIS actually had the initiative to conduct the measurement campaign related to aerosol in situ, aerosol remote sensing and modeling during the COVID lockdown in the period in May 2020. And the reasons was obvious scientifically, but of course they expected some kind of weekly reports to disseminate to national and international community. And of course this was a very good opportunity to test the community as a whole and to optimize some procedure within the EARLINET network. Within the EARLINET, we perform regular measurements 3 times per week. So it's related to daily measurements 2 times per week and 1 measurements during the night because of the Raman measurements that can be conducted only during the night because of solar or background. So the scope of the campaign was related to using or providing 2 types of data. First, we would like to allow fast analysis and status of the atmosphere during that period, and to do so, it was necessary to provide near real-time data, which are partially quality assured, and this data was used to provide weekly report in that period, and quick looks and reports were made public almost 12 hours after the measurements. So that was the first goal. And the second, which is still ongoing, is reanalysis the data with fully quality assured, and to identify possible changes compared to similar periods in previous years. And this data will be used to perform extended studies referring to the COVID-19 impact on the atmosphere. And this data can be used to compare to the climatology data, which have been observed during the last 10 or 15 years within the EARLINET. So this is the campaign work flow, how it was planned. Preparation phase was at the end of the April 2020. It includes instrument optimization because each lidar system is different, and it is necessary to perform and submit quality assurance tests. There are strict procedures within the EARLINET to provide quality assurance and quality control of the data. And the next step was to set up a single calculus chain configuration. What is single calculus chain? It is a tool provided within the EARLINET for automatic processes of the lidar data, and again it is specific for each lidar station. So it's very complicated to use and to provide the aerosol products, but therefore usually within the EARLINET the data processed within, let's say, a few months, but in this case we would like to provide near real-time data, so it was necessary to provide only level 1 data. That means that those data were not full quality assured. Then
your time is running short.
Okay. Then campaign started at 1st May and last until the whole period. And what was the measurement schedule? Well, each station provided 2-hour continuous measurements at noon and at nighttime conditions. And of course, the quality assurance related to dark measurements, telecover, rally fit, and polarization calibration had to be performed. So I'll skip these several slides. This is just a test related to Belgrade LiDAR station, and showing that we were able to provide reliable data up to the 10 or 15 kilometers, depending on day or nighttime measurements. The whole data were processed using single calculus change and available in near real time on the website. And Aerosol optical products that were published were particle elastic backscatter profiles, Raman backscatter and extinction profiles, and particle depolarization ratio. When we are talking about near real time, that means that we were able to provide results in maximum 12 hours after the end of each measurement. So in this slide, you can see the whole stations participating in this campaign. Yellow station measured 2 times per day, but there are several stations with quasi-continuous observations. And the whole products were made available at EARLINET Quick Look interface. Here you can see how it looks like. So you can select the station and check the whole products that were measured. Here you can see the data products calculated for each station during the daytime and night time. As you can see, for most stations during the nighttime, they were able to provide different products at different wavelengths. And here are some examples from Belgrade station for, let's say, May 7. As you can see, this is range corrected signals, and here you can see the aerosol layer at the lower troposphere, and here you can see the backscatter coefficients calculated using SEC. Here you can see the increase of the backscatter coefficients at the lower troposphere, which are directly related to the presence of the aerosols. What I should mention, yes, is that the weather conditions were not favor for the measurements, because there were dust intrusions and rain days. And here is example of dust intrusion on May 9. This is a dust regional atmospheric model forecast of the dust, and here you can see, our measurement during this 9 May. And here is the calculated backscatter coefficients. So the next was 14 May, similar situation. So it really influenced the whole measurement campaign. In this slide, you can see the statistics of all measurement stations, and out of, let's say, 1,300 scheduled observation, only about 700 were performed, representing 53%. And the reason was the bad weather, rain and low clouds mostly, where the LiDAR measurements couldn't be performed. Nevertheless, the 84% of the observed measurements were calculated using and perceived using SCC, and this is a very good score. And here is just a few examples of the preliminary results. Here you can see the monthly mean values of the aerosol backscatter coefficients at 532 nanometers. And you can see the differences between high troposphere and low troposphere during the daytime. You can see in Belgrade the differences. Here you can see the differences during the night time between the monthly backscatter coefficients at high troposphere and low troposphere. Of course,
could you please conclude?
Yes. Here you can see the optical products at the European scale for free and low troposphere, and this is just the differences for all station differences, the average of monthly for all station and climatological values for the period of the 200 to 2050. You can see that the low troposphere is a little bit more influenced than free troposphere. Here you can see the weekly differences, and again the average for all station, and the conclusion is that it's really hard to see the clear difference during the lockdown period and the climatological values. So it's related to the average values for all stations. So it's necessary to provide the more information for each site separately. Relating to scientific focus and impact, there are several other directions that we are working on, specifically comparison with satellite data, aerosol typing, and synergy with near surface and clouds. And now the reanalysis is performing, and in near future several publications will be provided at the end. So the aerosol backscatter coefficient is a proxy for the aerosol concentration. However, a more quantitative analysis must be made for each station, and this campaign was very useful because for the first time it is seen that the EARLINET can provide near real-time data, which can be very useful in emergency situation. The major results can be found in this publication. This is EARLINET internal reports, and it is publicly available. And at the end, I would like to thank all the EARLINET colleagues and ACTRIS and other supporting this campaign. So thank you. Sorry for the time.
Thank you very much, Zoran. I think it's very encouraging when one can participate to see how much results one can get out of measurements when one can participate in a Europe-wide experiment or campaign. So thank you very much. I am afraid no questions.